Hello guys, so this video is regarding the stress transformation in a body or stress transformation at a particular point in a element. Okay, so why do we need stress transformation first of all? So to understand this, what we need here is, see, in this body, if it is being subjected to all the forces, moments, external forces, so there will be inside this means at this cross section xx, there will be or yy, there will be moments and force reactions will be developing over here. So if you want to calculate internal forces and moments, just you cut it from here and just you can calculate the amount of forces and moments, and in means in results you can directly calculate the stresses and means normal stresses and shear stresses acting over here at this plane xx. Okay, so, but what happens if you want to calculate at the inclined plane, in this body, the stresses, the amount of stresses, normal stress and shear stress, and basically normal force and shear force is going to change because the plane is going to change. So this remember that the stresses will always be related to the plane on which they are acting, so that's why they are changing. So if you want to calculate means this plane is perpendicular to longitudinal axis, so this is basically what we call it as normal state or 0 degree at plane at 0 degree, and this is basically some transformed state or transformed plane at particular angle, that is basically theta angle from here, or you can just calculate it from the neutral axis or in anti-clockwise direction. So we take transformation in anti-clockwise direction as positive. So that is what is happening over here. So why do we do it? We want to calculate that what is the amount of maximum amount of stress at any plane. The maximum is amount of stress can be acting on any plane. So what we will do, we will develop relationship between this transformed stresses and the original stresses and the theta, and what we will do, we will differentiate these equation in terms of theta with respect to theta, and we will calculate the value of that theta on which these values of normal and shear stresses will be maximum, so that we can accurately design our mechanism or any body you want to design. So what we need is, we need maximum value of normal stress and shear. So that's why we are doing stress transformation. So that is what is it is, guys. So let's assume that this is the 2D state of stress at a particular element, okay, taken from a point in a body. So this is being subjected to means two normal stresses, means one normal stress and one shear stress at means positive x plane, and this is at positive y plane, and this is basically the similar things with the different means negative directions, means you can say minus in minus x and in minus y. And this we have know that due to complementary shear stress property, this tau xy acting on this plane, on this x plane, and on this plane will be, on y plane will be similar. Okay, so this is the transformed state. Basically we have denoted this normal stress and shear stress by prime, sigma x prime and x prime, means sigma x dash x dash x dash, okay, and tau x dash y dash. So this is the transformed stress. So now what we will do is, we will generate equations in terms of theta. So let's see over here. So what I have done is, basically suppose we want to the normal state of stress is that, and we want to calculate plane inclined at this angle. This is basically the same angle of theta over here. See the relationship, you can, this is 90 degree, okay, so you can just calculate the this theta will be equal to this theta. So that is what is happening. See this figure here. So what is happening is, if your plane is rotating over here, so this is basically the state of stress, rotated state of stress. So this plane is basically, this x plane is basically your now this transformed x plane like this. Okay, so what is basically this what we will do is, we will split this and resolve the components of these stresses so that we can directly get the values of transformed stresses like this. See, now what we have done in this figure is what I have done is this is your transformed axis x dash y dash, and this is your x and y, and the transformation is positive x theta in anti-clockwise direction. Okay, so suppose the area of this cross section is a delta a, so this will be automatically delta a sine theta, and this will be delta a cos theta. So remember this, okay, because we need that. And now what I have done is I have splitted this component, resolved the components of sigma xx and sigma yy. These are the original normal stresses, and this is for, in this figure I have done for normal stress, and in this figure I have done for shear stresses. Okay, so and by this way you can directly calculate the sum the all the forces acting in x dash direction, so that we can directly get the value of sigma x dash, and all the forward means sigma fy direction, the forces in y dash direction, you can directly calculate the value of tau x dash y dash. Okay, so make sure that you have to sum all the forces, means all the normal forces as well as the shear forces also. So first of all, what we have to do, we have to just resolve the component of these stresses, and these stresses, shear stresses, that you can see here, that this is sigma yy cos theta, sigma yy sin theta, sigma x cos theta, sigma x sin theta, and similarly for the shear stresses. Okay, now what we have to see over here is when we are summing over here, first of all what you have to do, you have to change the stresses into forces, because we cannot sum, because we have to sum the forces now. So we have to change the stresses into forces. So what we will do is we will just apply the into area, stress into area, this will become force, stress into area, this will become force. So you can see over here in this direction we are getting, so this is positive sigma x dash delta a minus this force, okay, into this area, and minus this force y, this force sigma y by sin theta into this area delta sin theta. So this is how we can calculate the equation, and see here, so this is your minus x dash direction, and this is also your minus x direction. So this is how we are getting tau xy sin theta, tau xy sin theta into a cos theta, and tau xy cos theta into a sin theta. So you can directly calculate the values and just multiply it with, and we are getting over here is this sigma x cos square theta, sigma y sin square theta plus 2 tau xy cos theta sin theta, and we know the identities here for the thetas, and we will replace them into lower terms, means we can directly calculate these, and putting these values, what we are getting over here is this equation. So this equation, what is basically, this is the transformed stress value, normal stress value, and this is the equation in terms of original stresses and theta. So at particular angle you want to calculate normal stresses, transform stresses and transform normal stress, you just put theta over here. What I want of the theta is means you are rotating, and just put theta over here. Suppose this is 30 degree, so just put theta, so this will be 2 into 30 into this will be 60, and this is also will be 60, and these are the original stress components. Okay, sigma xx, sigma yy. Okay, so just you can, this is how you can calculate the transformed values. And similarly, by putting by summing sigma means all the forces in y dash direction, you can directly get the values like this. Okay, so if you want, I also suggested that you do it with yourself, so that you can relate it, and also get means if you are getting confused, so you can get over it. Okay, so do it yourself, do this derivation yourself. And this, and what is this basically is see there, this, if this normal stress sigma x dash is varying, basically this is your normal stress, and this is also your normal stress, so this will be varying also, and this will be varying also. So how we will calculate this value? So what I have done simply is, since this plane, this theta plane, this axis plane, and this positive y plane is 90 degree apart, basically you can see here, The difference between these two angles, these two planes, is 90 degree apart. So if you want to calculate the values at this plane, you just, what you do is you just put 90 plus theta in this equation. So what I have done over here is this: just put 90 plus theta in this equation, you will get the value of sigma y dash from equation A. So this is what I have done. So this is how you can calculate transformed stresses. Next, what is basically is, you can see over here is that if your means transformation is negative, means in clockwise direction, so you have to put theta in negative sign, because we have derived these equations for positive theta and we have taken positive theta in anti-clockwise direction. Okay, so keep in mind, and this, all these means stress values are assumed as tensile stress. Okay, and this shear stress is taking upward positive, in positive y direction. Okay, so remember this. So if in the question or in exam that these values are different, means the direction is different, so you have to take care of this, you have to put with the sign. Okay, so that's the thing. So how to calculate maximum amount of this? So this equation will give you transformed stress, and what we will do now is we will calculate maximum value of the normal stress. Okay, so we are going to differentiate these equations, these two equations, in terms of theta. Okay, so this is how, what we have done is we have differentiated in with respect to theta, and what we are getting over here is we are getting over here the value of that theta on which normal stress will be maximum. Okay, so tan 2 theta p is equal to tau x upon sigma x minus sigma y by 2. Okay, so what is this? Basically this is the value you can calculate, and what we can do is, if we calculate this 2 theta p and put back in this equation, in A equation A, over here in this equation, in this, at this, we can just put 2 theta p and 2 theta p over here, cos 2 theta p and sin 2 theta p. We can calculate the value of maximum amount of normal stress. Okay, and because we have calculated theta, and then we can calculate the normal stress. Okay, so what we have done is, what I have done here over here is, we have just, if you don't want to use the identity, or you don't want to, means just basically sake of easiness, what I've done over here is, yeah, I've calculated sin 2 theta p and cos 2 theta p. So this is basically 2 theta p that you have been given, tan 2 theta p is equal to tau x. So this is perpendicular, this is base, and this is hypotenuse. Okay, so sin 2 theta p will be tau x upon this hypotenuse, and cos 2 theta p will be this base upon this hypotenuse, and just put the values in the equation. Okay, after the solving the equation, what we get is, we get sigma x dash is equal to sigma xx plus sigma y by 2 plus minus this. What is plus minus? Basically plus minus is basically the maximum and minimum principal stresses basically. So this is what we are getting. So from this equation we get two values of 2 theta p basically. Okay, in the equation. So there will be two principal stresses. So maximum normal stress is also called, principal stresses values. Okay, so sigma 1, sigma 2. So when we put positive we will get sigma 1, and when we put negative we will get sigma 2. Okay, and this sigma, this is how you can calculate the principal stresses. Okay, now what we have done is, we have put what you can do is, you can put this sin 2 theta p and cos 2 theta p in equation B over here, tau xy over here. So what you get is, you get that all the things will cancel out, and you will meet this equation, means the tau x dash y dash at the plane on which principal stresses are means normal stresses are maximum, on the plane of the principal stresses. So the shear stresses will be 0. Okay, so this is how what we have done. It means that at the plane of principal stresses there will only be normal stresses will be present, and shear, the value of shear stress will become 0. Okay, so after this, now we'll calculate maximum amount of shear stresses acting at any plane. So we have to know that plane angle. So just differentiating with the d theta. Okay, and just differentiating. So what we are getting over is, this is the 2 theta s. At 2 theta s we are having the value of, at 2 theta s we will put the value over here in the back in the equation and calculate the maximum amount of shear stresses. Okay, so we'll calculate similarly we can calculate the value of sine 2 theta s cos 2 theta s like this. Okay, so this is basically 2 theta s, and this is perpendicular, and this is base, this is perpendicular, this is base, and just you can calculate the value. So there will be two values over here also, 2 theta s1 and 2 theta s2. Okay, so because they are two positive phase and negative phase. Okay, that is why we are getting two values basically. So after putting this tan 2 theta s, or you can say sin 2 theta s and cos 2 theta s back in equation b, means in here in this equation, just put the value of sin 2 theta s and cos 2 theta s. Okay, and what we are getting over here is, we will get this equation. Okay, so this is equation you can calculate maximum amount of shear stress that can be acting at a certain plane. Okay, and what is the plane, or what is that plane, what is the angle of that plane? That plane angle will be theta s or 2 theta s. Okay, so theta s will be somewhere, means what it indicates that at certain angle of plane of theta s there will be shear stresses will be maximum. Okay, and one thing more, that if you want to calculate means if we put this value sin 2 theta s and cos 2 theta s in equation a, means this in normal stress. So what we are getting over here is that there is a value is coming over as sigma xx plus sigma yy by 2. So what it means is that at the plane of maximum shear stress, at the plane of maximum shear stress, there will be a normal stress will be present. However, that's not the case with this principal stress plane. Okay, at 2 theta p means at the plane of principal stress there will be only normal stress will be present, shear stress will be 0. But at the plane of maximum shear stress will be present, also normal stress is present, and that normal stress is basically called as sigma average. This is the minimum normal stress is present over there. So also there is one identity also is there, that the difference between theta p and theta s will always be 45, or 2 theta s and 2 theta p will always be 90, so that you can check the values. Okay, if after the calculation you can check the value. This is the identity basically. How it is becoming basically, just multiply these two, tan 2 theta p multiplied by tan 2 theta s, and you will meet with the -1. So that is how we can calculate. Okay, so this is the identity. So just go through the examples over here. Okay, and we'll meet in the next lecture. So that is basically a Mohr circle. So let's finish this. So what is Mohr circle basically? Mohr circle is the representation of transformed stresses in terms of graph form. Okay, so Mohr has given the graphical solution for the transformation. Okay, so one can use equations and one can use graph in order to calculate the transformed stresses or maximum amount of principal stresses. Okay, so let's suppose this is our normal state of stress, and this is our at some inclined plane or at some transformed angle. This is angle theta. So these are the stresses. So what we have done is, we have already calculated the equation in terms of theta normal, means original sigma x sigma y at normal state of stress, and this is the theta. Okay, so just what you have to do is, you have to rearrange the terms, and after rearranging, what we are having here, this is a transformed stress, normal stress, and this is transformed shear stress, and this is what we have done is rearrange the term. We have just put this term in on left hand side and just adding these two and squaring these. So what, first of all you have to square then add. Okay, so that's what we have done over here. So what we are getting over here is, we are getting this equation. okay. And this equation is very similar to the equation of circle, okay. And what this means basically, so at this circle you can see this circle, the radius, which radius is radius, the value of radius can be calculated from here. And what is the center of this circle? Center of the circle will be given by this. So if we plot between normal stress and shear stress, and why I have taken downward positive, I will tell you later. That normal stress and shear stress, if we plot this equation, we will get a circle. And what its circle is basically the points. The point of this circle denotes the value of stresses at a plane, okay. And which plane? This plane, A plane and B plane, okay. So at each plane, at each point, the value, this ordinates x and y, or you can say sigma xx and tau xy, this will defines the value of the normal stress and shear stress at each point. Means at this point this will be different, at this point this will be different. You are getting the means. If you are going to transform this, so how we can calculate, or how we can draw it, basically is very simple. So what you have to do is, first of all, you have to see what are the at original state of stress, what is the amount of the value of normal stress and shear stress, okay. And this is your A plane, positive x plane, and this is your positive y plane, let's call it as B. So what you have to do is, you have to plot this basically. So in this positive x plane, this will be positive and this is positive, okay. And in this plane means what we take is, we take anti-clockwise positive. So anti-clockwise shear stress will be positive and clockwise shear stress will be taken as negative, okay. So this is how we draw the thing. So what you have to do is, you have to just plot these ordinates, sigma xx tau xy and sigma yy minus tau xy, okay. Because this is at this plane, this will be clockwise in nature, so this will be clockwise, shear stress will be clockwise, and this is normal stress. And if this normal stress sigma x is incompressible in nature, then you have to means plot accordingly. This will be getting over here, okay. So just plot A point and B point, then just draw the line between them, and where this line is cutting over here, this will be the center, and this you can accurately calculate with the equation also. So this will be the center of the circle. And what is this basically? See this, if you put perpendicular over here, this will be tau xy and this is your base, and this hypotenuse is basically the radius which you have calculated over here. So this is how you can calculate graphical. So just plot a graph over here, plot the this axis, normal stress and shear stress, and just plot the points over here and join them. And then by means putting over the compass over here at C, and pencil over here at A, just draw a circle, okay. And where this circle meets over here at 0, what it means over here, and at this point, what is this? Each and every point is a plane, basically at each and every point on this circle is a plane, and this plane is a plane, and each and every point will give you the different values, okay. So at this point, what is happening over here, there is no shear stress. See, this will be sigma and this will be 0. So what this means is, this at this particular plane, at this particular point, this particular point is basically the point of principal stresses, okay. Let's go further over here. Let's see, these are the steps that I have already given, that you can go through and just calculate this. So why I have taken means positive tau downwards. See what is happening over here is, I have taken transformation anti-clockwise positive over here. So for doing the same thing over here, I have taken tau in this direction, okay. So this is your A, original state of stress after transformation at 2 theta, okay. So why we are taking 2 theta over here? See the things over here. See the plane, the angle between the plane A and angle between the plane B, okay. So what is the difference? 90 degree. And here what it is there, the plane angle between A and plane B is 180 degrees, so the twice the difference is there. Okay, so whatever the transformation you are doing here in the state of stress, you have to do twice the angle. Okay, you have to use 2 theta over here in the Mohr circle, so that's why we do 2 theta. Okay, and A dash, so this will be your transformed stresses. Transformed stresses will be there, and B will be your uh, positive Y phase. Okay, and this is 2 theta 2 theta. So here also you just put 2 theta over here and draw a line where the line is cutting over here. This will be your transformed stresses, and this will be your transformed stresses at B dash, and this is your transformed stresses at A. Okay, so this is how you can calculate the values of transformed stresses. Also you can calculate the value of 2 theta P. So 2 theta P will be the angle between the normal state of stress and this horizontal line. Okay, so this is the value of principal stress, sigma 1 0, sigma 2 0, and this is the value of maximum shear stresses. So maximum shear stress will, where it will be, it will be maximum over here. So this is the value of maximum shear stress. Just put a perpendicular line over here and you can calculate the value of maximum shear stress. The funny part and the fact part means you can say funny part is that the maximum value of maximum shear stress, sorry, the maximum value of shear stress will always be equal to the radius of the circle. Yeah, that's the thing. And this points donates sigma y because this is the center. Okay, and this is your shear stress, and the value of 2 theta s, the value of the plane of the maximum shear stress will be calculated by here. Means you can calculate it by here 2 theta s from the normal state of stress. So this is how you can calculate by Mohr circle. This is very easy, and just you have to plot the points and just you have to join the line and draw the circle. And what you have to careful about that in plotting, that you have to see whether it is tensile or compressive. According to that you have to change the sign. So I have means we have transformed the, we have done the equation, we have reduced the equation in terms of normal stress and shear stress that are basically positive. Okay, so if it is negative means the direction is different, so you have to take care of this. You have to put a negative sign over it. So you have to, if it is, if sigma axis is negative, so it will come over here because this is negative x-axis, this is positive sigma axis, and this is positive tau axis. So according to that you have to deal with it. Okay, so hope it clears the transformation part, and in next part we will go for bending moment and shear force. Okay, thank you.